Hello, everybody. So I hope you're doing well. Today, I would like to talk about aromaticity and the famous Huckel 4n plus 2 rule. Okay, so let's remember that aromaticity is a special stabilization over and above the stabilization that is conferred by resonance alone that is enjoyed by certain kinds of molecules. Benzene is the preeminent aromatic molecule. Benzene is the aromatic molecule par excellence. Last time, at our last discussion, we were talking about molecular orbital theory, or I think maybe a couple of discussions ago about molecular orbital theory. And we were talking about the molecular orbital theory of cyclic systems, such as benzene. So let's just briefly recap what we said at that time. Is the electrons in atoms and molecules are waves. And waves have an amplitude, they go up and they go down. They have a positive deflection and a negative deflection. And another characteristic that is important about waves is that the number of nodes that a wave has correlates to the energy of that wave. More nodes equals more energy. And what is a node? Well, remember, a wave has to go up and a wave has to go down. In the journey from the positive deflection to the negative deflection, in the transit from the positive number to a negative number, has to pass through zero. So that's what a node is, where the wave is equal to zero. And the more nodes a wave has, the more energy that wave has. And molecular orbitals and atomic orbitals as well share the same characteristic. More nodes equals higher energy. Okay, so last time we were talking about how to draw the molecular orbitals. And let's just briefly recap for benzene. So the fundamental principle here would be that the number of interacting p molecular orbitals, the number of p orbitals, that will equal the number of pi molecular orbitals. In benzene, we have 6 p orbitals, one on each carbon. And so we expect 6 pi molecular orbitals. And they differ one from the other in terms of the number of nodes each has. And that is also the difference in their energy. So if we look at benzene, we can draw it in a couple of different ways. So there's the Kekulé structure of benzene, right? And this is the same as when we look at the interacting p orbitals. All of the carbons in benzene are sp2 hybridized. They all have a p orbital. And so that's just a rough sketch of the molecular orbitals of benzene. But this takes a lot of time. To draw this requires a certain amount of artistry. So I'm going to change that up in where I'm looking at the orbital from the top. That's my eye. That's supposed to be my eye. And so all I see are the tops of these p orbitals. That just is much faster to write. So I'm looking at the top of the p orbitals. I see that. So this lack of shading, let that represent positive deflection, right? Because a wave, remember, it goes up and it goes down. So these are positive algebraic sign numbers. And the shaded portion, let that represent negative deflection or negative algebraic sign numbers. So this is the representation that I'm going to be using today mostly. And now when it comes time to drawing the molecular orbitals, what we start with is a molecular orbital that has 0 internuclear nodes, and then we start adding nodes in a symmetrical fashion. And so the next highest energy molecular orbital will have 1 node, then the next highest will have 2 nodes, 3 nodes, and so on and so forth. What the problem boils down to is how many ways can you draw a dotted line representing a node through a hexagon. Okay, so still recapping what we talked about last time. I'm going to erase all of this. Okay, the lowest energy pi molecular orbital of benzene will have 0 internuclear nodes. And so again, this representation, what do these circles mean? Those are the tops of the p orbitals. Then the next highest molecular orbital is going to have 1 node, and the problem is how can you draw a dotted line through a hexagon in a symmetrical way? So there turn out to be 2 ways of doing that. You could do this, and you could do that. Okay, so this dotted line represents the nodal boundary. And so the molecular orbital is going to be positive on one end of this, on one side of this dotted line. It's going to be negative on the other side of this dotted line, because there the wave is passing through positive deflection to negative deflection. So this molecular orbital looks like this, where again the open circles represent the top of the p orbitals, positive algebraic sign. The shaded circles represent the tops of the p orbitals, negative algebraic sign. And over here we would have positive on one end and negative on the other end. Okay, now the next molecular orbital, remember we're expecting 6. The next molecular orbital is going to be a hexagon with 2 dotted lines drawn through it. So how could I do that? I could do this. And I could do that. Okay, a cross and an X. All right, so positive, negative, positive, negative. Over here, positive, negative, negative, positive, negative, negative. Okay, so that's 2 internuclear nodes. 5 orbitals down, 1 to go. The highest energy molecular orbital is going to be a hexagon with 1, 2, 3 dotted lines drawn through it, representing the nodes. And so I'm switching the shading every time I cross a dotted line, because that's where the node is. Okay, so there's a representation of the 6 pi molecular orbitals of benzene. Now it's time to feed in electrons. And we feed in electrons in accord with the Aufbau principle, Pauli exclusion, and Hund's rule. So maybe you remember all this stuff from Gen Chem. What does Aufbau principle say? Electrons occupy orbitals in order of energy, low to high. What does Pauli exclusion say? No 2 electrons can have all 4 quantum numbers in common. Another way of saying the very same thing is that the maximum number of electrons that can live in the same orbital is 2. And what does Hund's rule says? Maximize the number of spin-up electrons while observing and holding to Aufbau and Pauli exclusion. Okay, so we're ready to feed in electrons to benzene. How many electrons do we feed in? 6. Because, let me see, just over here. Right, there's benzene. You see this line right here? That represents 2 electrons in a pi orbital. See this line over here? That represents 2 electrons in a pi orbital. See this line right here? That represents 2 electrons in a pi orbital for a total of 6 electrons. 1, 2. See, I'm following Aufbau. I put the first 2 electrons in the lowest energy orbital. I put one spin up and one spin down, and I can't put any more electrons in this orbital. It's full. 3, 4. See how I'm following Hund's rule? I'm maximizing the number of spin-up electrons while observing outbound and Pauli exclusion. 5, 6. Okay, so there's the the electron occupation of benzene. Okay, and from this picture, we understand the theoretical concept of aromaticity, which is that an aromatic molecule has a full closed shell of pi electrons. And so this is the very same reason that the noble gases, xenon and argon and so on, that's why they're so unreactive. That's why they're so stable, because they have a full shell of electrons. But when it comes to aromaticity, it's going to be this the pi molecular orbitals that are full. Okay, so that's for benzene. Now, if we do this for if we do this for the 3-membered ring, the 4-membered ring, the 5-membered ring, the 6-membered ring, 7-membered ring, so on and so forth, if we do this for a lot of different systems, a pattern emerges. Okay, and that pattern is you have a unique lower energy orbital, right? Just like the benzene diagram. And then they pair up like this. Dot, 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 dot. So that, you know, in the general case, you have a unique lower energy orbital, and then the orbitals pair up like that, because there's going to be 2 ways of drawing a dotted line. There are going to be 2 ways of drawing dotted lines through these polygons. Okay, and so to have a full shell, you need 2. Oh, that's a full shell. 2 is an aromatic magic number. Okay, the next aromatic magic number would be 6. 6 is an aromatic magic number. The next magic number would be 10. That's a full shell. 10. The next aromatic magic number would be 14. And this is the origin of the Huckel 4n+2 rule, which now we can state. To be, or not to be, aromatic. To be aromatic, you must have a planar cyclic array of p orbitals, right? That's what benzene has, is all of the atoms, all of the carbon atoms of benzene are sp2 hybridized. The sp2 hybridization state is trigonal and planar. It has a planar cyclic array of p orbitals. And in that array, there will be 4n plus 2 pi electrons. Okay, so this formula and this n causes no end of confusion. N is not the number of carbon atoms. N is not the number of double bonds. N is not the number of electrons. N is none of those things. N is an integer that, when you plug into this formula, generates the aromatic magic numbers. So that, you know, that's just terminology I developed. Magic numbers, the aromatic magic numbers. What are they? Plug a 0 into this equation, what do you get? 2. Plug a 1 into this equation, what do you get? 6. 2, 6, 10, 14, and so on and so forth. So notice these are, another way of remembering these numbers is that these are the odd multiples of 2. 1 is an odd number. 1 times 2 is 2. That's an aromatic magic number. 3 is the next odd number. 3 times 2 is 6. 6 is an aromatic magic number. The next odd number is 5. 5 times 2 is 10. That's the next aromatic magic number. Okay, so this is the criterion for aromaticity. And remember, aromaticity is the property of a stabilization over and above, greater than, in addition to resonance stabilization. There is a counter image to this, and that is to be anti-aromatic. What does anti-aromatic mean? Molecules that are anti-aromatic are destabilized to an extraordinary degree, right? So aromatic molecules are stabilized, anti-aromatic molecules are destabilized. And to be anti-aromatic, a molecule must have a planar cyclic array of p orbitals. But this time, to be anti-aromatic, it's 4n pi electrons. And again, this n in this formula causes no end of confusion. It's not the number of pi bonds, it's not the number of carbon atoms, it's not the number of double bonds, it's none of those things. It's just a series of integers that, when you plug them into this formula, generate the anti-aromatic magic numbers. So n here could equal 1, 2, 3, so on and so forth. So the anti-aromatic magic numbers, are 4, 8, 12, etc. These are the even multiples of 2. 2 is an even number. 2 times 2 is 4. The next even number is 4. 4 times 2 is 8. 8 is an anti-aromatic magic number. The next even number is 6. 6 times 2 is 12. 12 is an anti-aromatic magic number. So this is the lowdown of how you can predict whether something will be aromatic or anti-aromatic. If any of these conditions are not met, the molecule will be non-aromatic. Okay, so let's do some problems. Oh, but before I do that, where does this anti-aromatic comes from? Well, when we go back, remember I said that this was the pattern when we do draw those polygons and draw those dotted lines through the polygons and draw the molecular orbitals. This is the pattern that emerges. An anti-aromatic, the first anti-aromatic number is 4, so that would mean an occupation diagram looking like this. And what we see here is an exactly half full shell of pi orbitals. And there's something about being half full that is destabilizing. And so that is the observation that when the molecule has a half full shell of electrons in these pi orbitals, the molecule is destabilized to an extraordinary degree. Okay, the next anti-aromatic magic number is 8. 6, 7, 8. Oh, okay, there's another half full shell. The next anti-aromatic number is 12. Oh, okay, there's 12. There's the next anti-aromatic magic number. So there's something about being exactly half full that is destabilized. Okay, so let's do some problems. Okay, so what about this molecule? Let's classify it as aromatic, anti-aromatic, or non-aromatic. So what do you think? Aromatic, anti-aromatic, or non-aromatic? Oh, it's non-aromatic, because to be aromatic, the molecule must have a planar. Can this molecule be planar? Oh my heavens, yes. All of these atoms are sp2 hybridized. This thing can be planar, but it's not cyclic. Cyclic means a closed loop of p orbitals. You're looking for a donut. You're looking to be able to put your pencil down and come back without lifting your pencil to the very same place you started with. Okay, so this is not, it's planar, but it doesn't have a cyclic array of p orbitals. Okay, so this is planar. Check. Is it cyclic? No. How many pi electrons are there? 6 pi electrons. So that's an aromatic magic number, but this molecule isn't aromatic because it's not cyclic. So this is non-aromatic. Yes? Okay, so let's try another one. Okay, what about this guy? Is he aromatic, anti-aromatic, or non-aromatic? Are you trying it out? Yes? Oh, he's another non-aromatic molecule, because that's an sp2 hybridized atom. There's the top of the p orbital. That's what that circle represents. There's a p orbital there. There's a p orbital there. There's a p orbital there. Uh-oh. This carbon at 12 o'clock, he's sp3 hybridized, and there is no p orbital there. And so you're looking for a donut of p orbitals. This is a horseshoe, right? This is a horseshoe. It's planar, but it's not cyclic. And how many pi electrons in this thing? 4. So this is non-aromatic. Okay. All right, so now let's try. Let's try that. So tell me, is that aromatic, anti-aromatic, or non-aromatic? He's aromatic because he's a cyclic array of p orbitals. Every carbon atom is sp2 hybridized. Every carbon atom has a p orbital, and it's a cyclic planar array of p orbitals with 10 pi electrons in it. See this line here? That represents 2 pi electrons. 2, 4, 6, 8, 10. 10 pi electrons. And there's a p orbital there, there's a p orbital there, there's a p orbital there, 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 p orbital there. And you're looking for a donut. This is like a donut that maybe an elephant sat on. But if I start here, I can, without lifting my pencil, just trace out a loop and return to my original location. So this guy is aromatic. And so there's something unusually stable about aromatic molecules, and this would be one of them. Okay, so let's try another one. How about it's a 7-membered ring fused to a 5-membered ring with the double bonds deployed in that manner. So tell me, is that aromatic, anti-aromatic, or non-aromatic? Oh, that's another 10 pi electron aromatic system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it planar? Yep. Is it a closed loop? Yep. So this is an aromatic 10 pi electron system. Okay, so now let's ratchet up the level of complexity a little bit more, one more notch, and let's talk about what would happen if a triple bond were involved in the structure. Okay, so I'm going to draw a molecule that has a triple bond. I'm going to talk about how to count up electrons in a triple bond. So this is not the easiest thing in the world to draw. Okay, what about something like that? Would that be aromatic, anti-aromatic, or non-aromatic? So what I'm talking about now is how do you count a triple bond if one is insinuated in the structure? So remember back in Gen Chem when you were studying the geometry of the triple bond, maybe somebody told you that a triple bond has 2 pi bonds and 1 sigma bond. And the 2 pi bonds are mutually orthogonal. You have an up and down pi and an in and out pi. Okay, so focusing on this triple bond up here, you have an up, you have an in and out pi. Remember, this circle represents the top of the p orbital. So this is a p orbital that is sticking out of the plane of the blackboard and behind. So this is an in and out p orbital. And then you also have an orthogonal, pi bond. And so that would be in the plane of the P, right? So remember this from Gen Chem, you triple bond, you have a sigma bond, you have an up and down P and an in and out P. Up and down P, in and out P. Up and down P, in and out P. Up and down P, in and out P. Okay, so this guy here, he's sp2 hybridized. There's a p orbital there, 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 p orbital there. Okay, and so we see that this molecule has a planar cyclic array of p orbitals, but that planar cyclic array is only the circles, the in and out p orbitals that are interacting to form the pi bond. So the in and out p orbitals, they are counted. The side-to-side p orbitals, they are not counted because they do not participate in the planar cyclic array. Okay, so how do you count a triple bond? A triple bond counts the same as a double bond. It contributes 2 electrons to the pi system of the planar cyclic array. Okay, so with all that out of the way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's a 16 pi electron system. Is that aromatic, anti-aromatic, or non-aromatic? Well, 16 is an anti-aromatic magic number. So this would be anti-aromatic. Right, it's 8 times 2, and 8 is an even number. The anti-aromatic magic numbers are the even multiples of 2. The anti-aromatic molecule par excellence. Oh, this chalk's killing me. The anti-aromatic molecule par excellence is cyclobutadiene. P orbital there, P orbital there, P orbital there, P orbital there. It's a 4 pi electron system. It's planar, it's anti-aromatic. And just to give you an idea of how unstable an anti-aromatic molecule is that this molecule cannot exist above 4 degrees Kelvin, right? I didn't say 4 degrees Celsius. I said 4 degrees Kelvin. So this molecule reacts, or it falls apart, or it does something. It can't live above 4 degrees Kelvin because it's so darn unstable, because it's anti-aromatic. The truth is, there are very few anti-aromatic molecules. Molecules want to be aromatic, they don't want to be anti-aromatic. So that coming up with an anti-aromatic molecule, that's very hard to do, because the molecules are trying everything to avoid having a planar cyclic array of p orbitals with an anti-aromatic magic number within. The preeminent example of that is cyclooctatetraene. See, I'm looking at that and I'm seeing, oh, p orbital there, 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 p orbital there. 1, 2, 3, 4, 5, 6, 7, 8 electrons. If this were planar, it would be anti-aromatic. It's an 8 pi electron system. It's anti-aromatic if planar. But molecules will do practically anything to avoid being anti-aromatic. There are very few anti-aromatic molecules because molecules don't want to be anti-aromatic. This guy is flexible enough that instead of being planar, it adopts what is called the boat or the tub conformation. So in order to avoid being planar, in order to avoid being anti-aromatic, the molecule actually puckers into this tub. So is this molecule anti-aromatic? Is cyclooctatetraene anti-aromatic? No, it's non-aromatic. Non-aromatic. Why? Not planar. So coming up with anti-aromatic molecules is very hard. On a test, it will probably say, assume that the molecule is planar, right? Because it's very hard to predict whether some molecules are planar or not, especially in more advanced cases. So if you're taking a test and you see this molecule and the instructions to this question said, assume it's planar, the correct answer is anti-aromatic. But in fact, it is not anti-aromatic because it's not planar, because molecules try to do anything to avoid being anti-aromatic. All right. Next level of complexity, let's talk about carbocycles that have a charge on them. What about that molecule? Is it aromatic, anti-aromatic? Is it aromatic, anti-aromatic, or non-aromatic? See those two positive charges there? Yeah. So what about it? Is it aromatic, anti-aromatic, or non-aromatic? Oh, this is a 2 pi electron aromatic system. 2 pi electron aromatic system. Okay, so that's an sp2 hybridized carbon. There's a p orbital there. That's the top of the p orbital. Same goes here. This is a carbocation. What is the hybridization state of a carbocation? sp2. There's a p orbital there, but it's empty. Right? That's why it's a carbocation. That's why it has a charge on it. And same goes for this guy. So I see a planar closed loop of p orbitals. And how many electrons live in this p orbital? 1, 2, plus 0 is still 2, plus 0 is still 2. It's a 2 pi electron aromatic system. And one of the amazing things about this molecule is that we would ordinarily never tolerate two positive charges being close together, right? Because positive hates positive. Like charges repel. In an ordinary molecule, we would never tolerate these two positive charges. But here, the stabilization of aromaticity overwhelms the Coulombic repulsion caused by two positive charges. So this guy, he's a real molecule. He's been synthesized, and he's unusually stable, even though he has those two positive charges next to each other. Okay, what about this guy? Is he aromatic, anti-aromatic, or non-aromatic? Is there a planar closed loop of p orbitals? Yes. How many electrons live in that planar closed loop of p orbitals? 4. This is an anti-aromatic molecule. P orbital there, p orbital there, p orbital there, p orbital there, p orbital there. So there's my planar closed loop of p orbitals. 1, 2, 3, 4. Empty, still 4. 4 pi electron anti-aromatic system. This molecule is extremely unstable. It has been synthesized, it does exist, but it cannot live above about 70 Kelvin, right? So very, very unstable molecule. Okay, what about something like this? I want an 8-membered ring. Double bond, double bond, double bond, negative and negative. Uh-oh, 2 negative charges right next to each other. That's very bad, isn't it? So is this aromatic, anti-aromatic, or non-aromatic? This would be a 10 pi electron aromatic system. So we have a p orbital there, a p orbital there, p. All of that is easy because we're just looking at an sp2 hybridized atom. This negative charge now, that means there are 2 electrons there. That's why it's negative, and they live in a p orbital. 2 electrons there, they live in a p orbital. So total number of electrons, 2, 4, 6, 8, 9, 10. So this is a 10 pi electron aromatic system, right? 10 is an aromatic magic number. And once again, is that we would never tolerate those 2 negative charges being close together like this. But the stabilization of aromaticity overcomes the Coulombic repulsion. So this molecule is real, it has been synthesized, it's unusually stable. So how'd that go? All right. Next and final level of complexity is what happens when the cycle has an atom other than a carbon atom in it. It could have nitrogen in it or oxygen. Okay, and so most people find this pretty difficult to understand. So let's go through a bunch of examples. Water. What is the hybridization state of the oxygen atom in water? sp3, right? That's sp3. How many p orbitals, up and down or in and out or side to side or whatever, would we find on this oxygen atom? 0. There are no p atomic orbitals on that oxygen. They've been hybridized out. Okay, now, so we know that maybe since high school, right? So now let's change this up a little bit. Looks like water so far. But now I'm going to put it into this ring. What is the hybridization state of this oxygen atom here now? Is it still sp3 like the oxygen atom in water? Oh no, this is sp2 hybridized. There are 2 pairs of electrons, 2 unshared pairs of electrons, but if the oxygen is sp3, it would be non-aromatic because the sp3 hybridization state doesn't have a p orbital. So there would be a p orbital there, a p orbital there, a p orbital there, a p orbital there, no p orbitals there. You're looking for a donut of p orbitals to be aromatic or anti-aromatic. This would be a horseshoe. But if the oxygen is sp2 hybridized, then it becomes a 6-pi electron aromatic system. And molecules want to be aromatic if possible. They want to enjoy the special stabilization of aromaticity. There's a p orbital there, there's a p orbital there, there's a p orbital there, there's a p orbital there. This oxygen is sp2 hybridized. One of these electron pairs is in a p orbital. There's my closed loop. There are my 1, 2, 3, 4, 5, 6 pi electrons. No molecule wants to be anti-aromatic, right? They try to avoid being anti-aromatic at all costs so that we don't see a changeover of hybridization state from what we're expecting based on general chemistry, high school chemistry type considerations. We don't see a changeover to make the molecule anti-aromatic. Molecules desperately want to avoid being anti-aromatic. Okay, so just to summarize what we're talking about is that if the cycle has an oxygen, nitrogen, sulfur, whatever, and if it can contribute an electron pair to the pi cycle such that we get an aromatic magic number of pi electrons, it will do so. All right, so let's talk about more examples. Okay, so what about this guy? Is he aromatic, anti-aromatic, or non-aromatic? Let me rephrase the question because this is now we're getting into something kind of complicated. Let's just ask the question, is he aromatic? Right, we can make it a little simpler that way. It's either going to be aromatic or it's not going to be aromatic. Let's forget about anti-aromatic and non-aromatic for the moment. So this oxygen has 2 unshared pairs of electrons. This nitrogen has 2 unshared pairs of electrons. There's a sp2 hybridized carbon there, sp2 hybridized carbon there, sp2 hybridized carbon there, sp2 hybridized carbon there. To be aromatic, to get an affirmative answer to this question, we need a donut of p orbitals with an aromatic magic number of electrons in there. So if this nitrogen puts these two electrons into a p orbital, we still don't have the donut, we just have a horseshoe now. If this oxygen puts this electron pair into a p orbital, now we have the donut. How many electrons living in that donut? 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's an anti-aromatic magic number. Molecules don't want to be anti-aromatic. So is this molecule aromatic? No. The reality is this molecule is non-aromatic because it is not planar. The actual shape of this molecule is looking something like this. Kind of looks like a chair. Because no molecule wants to be anti-aromatic. Right? This thing isn't going to become anti-aromatic just because it's going to fit the rule that we're talking about. So it distorts from planarity. So this molecule is actually non-aromatic. On a test, if the instructions to the question say, assume that the molecule is planar, the correct answer here would be anti-aromatic. But in reality, the molecule is not anti-aromatic. It is non-aromatic because it distorts away from planarity. Not always easy. Okay, let's try another one. Okay, so what about something like this? And again, let's table for the moment whether it's anti-aromatic or non-aromatic. Let's just see, does it fit the bill to be aromatic? Okay, so this nitrogen has an unshared pair of electrons there. This oxygen has two unshared pairs of electrons there. This nitrogen has an unshared pair of electrons there. Now, this causes no end of confusion, right? P orbital there, P orbital there, P orbital there, P orbital there on the nitrogen. Notice this unshared pair of electrons on this nitrogen is not in the P orbital. Right? See this line right here? That means there's a P electron on this carbon interacting with the P electron on that nitrogen to form that pi bond. And if you think back to Gen Chem, you know that the P orbitals are orthogonal, up and down, side to side, and in and out. This circle represents an in and out P. These dots are not in an in and out orbital, P or otherwise, because no hybridization state has two up and down P's, right? One P orbital is up and down, one P orbital is side to side, and the other P orbital is in and out. So yes, this nitrogen has an unshared pair of electrons on it, but this is not in a P orbital. This nitrogen has a P orbital. We know what it's doing. It's involved in pi bonding with this carbon. Okay, slam this into a P orbital, slam that into a P orbital. So how many so there's my donut. How many electrons living there? 1, 2, 3, 4, 5, 6, 7, 8. Right, so this would be anti-aromatic if planar, because it's an 8-pi electron system. But again, this molecule distorts from planarity. The actual shape of this molecule, it kind of looks like our old friend, the Diels-Alder diene, right, with a nitrogen here And then this nitrogen is there, and then whoa, down. Kind of an ugly drawing, but it's not plain. Oh yeah, more. What about this guy? Right, and not doing you any favors, but I'm going to draw in all of the unshared pairs of electrons, right? I'm doing this to trick you and to confuse you. I'm not doing you any favors here by showing you all these dots. Because when the ring contains an atom other than carbon, we have to carefully assess whether those dots are in a p orbital or whether they aren't in the p orbital. That's the crisis. So what about this guy? Is he aromatic? What do you think? Oh, he's aromatic, all right. He's a 6-pi electron system. Aromatic, yes, 6-pi electron, and also a planar closed loop. There's a p orbital there. There's a p orbital there. Okay, but now everything else is going to be a crisis. See this line here? That means there's a p orbital on this nitrogen with an electron in it interacting with a p orbital on the carbon with an electron in it. There's a p orbital on this nitrogen atom. We know what it's doing. It's forming the pi bond to the neighboring carbon. But this unshared pair of electrons is not in a p orbital, in and out or otherwise. It's in an sp2 hybrid atomic orbital. Right, because no hybridization state has two up and down or two in and out p orbitals. The sp hybridization state has an up and down p and an in and out p, but no hybridization state has two up and down or two in and out p orbitals. So there's a p orbital there. We know what he's doing. He's making a pi bond to the neighboring carbon. These guys can't be in a p orbital that is also in and out. Same goes for this guy. These electrons aren't in a p orbital. There's a p orbital on this nitrogen. He's busy forming a pi bond to this carbon. All right, so there's our closed loop of p orbitals with 1, 2, 3, 4, 5, 6 pi electrons in it. Is it aromatic? Oh, you bet. Okay, how about the next and final level of complexity? How about let's put in an atom other than carbon and also a charge. So what about him? Is he aromatic? Is he aromatic? Oh my heavens, yes. He's a 6-pi electron system. P orbital there, P orbital there, P orbital there, P orbital there. Unshared pair of electrons on that nitrogen. If I drag them into a p orbital, there's a p orbital up here, but it's empty. I have 1, 2, 3, 4, 5, 6 plus 0 is still 6. He's a 6-pi electron aromatic molecule. Okay, let's try one more. So it's, no, And once again, just to confuse you and just to throw you off the scent, I'm going to write in all of the unshared pairs of electrons. When you have nitrogen, oxygen, sulfur, the crisis is, are those electrons in a p orbital or aren't they? So is this aromatic molecule? No, this molecule is known, and this is one of the very few examples of something that is actually anti-aromatic. It's an 8 pi electron system. It doesn't have the flexibility that cyclooctatetraene does. It can't distort away from planarity. So this is actually anti-aromatic. It's one of the few molecules that is known to be anti-aromatic. It's an 8 pi electron system. So let's see where we came up with that. P orbital there, 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 P orbital there. That's easy. There's a P orbital on this nitrogen, but the electron in the P orbital on this nitrogen is busy forming the pi bond to the neighboring carbon. So these two electrons are not part of the donut of p orbitals. Okay, there's a p orbital on this oxygen, and he's busy forming the pi bond to the neighboring carbon. And there is no hybridization state that would have two in and out p orbitals. So once again, this pair of electrons don't belong to the pi cycle. How many electrons? 1, 2, 3, 4, 5, 6, 7, 8, and we're back again. So this is one of the few examples of an 8 pi aromatic system. Okay, so that's all I have for you today, unless you have any questions for me about anything. Any questions about anything? Very well, I'll see you next time. Until then.